we have come to what I think is one of the most interesting chapters of the quarter. The ideas and concepts we learn in this chapter will explain so many of the things you see in your everyday life. Credit cards, motors, and how the electricity you have in your house is generated. So let's take a look at electromagnetic induction. If I have a wire loop set up like this perpendicular to the page, and it's hooked up to an ammeter, well, there's no source of EMF. There's no battery hooked up to this loop. There's no current flowing in it. But if I take a magnet and I move it toward the loop like this, then current flows in the loop. And the ammeter would read some current flow in this direction. Now we're just going to stop the magnet in front of the loop. We brought the magnet in, and while the magnet was moving toward the loop of wire, current was flowing in the loop of wire. Without a battery, without a source of EMF, current was flowing through that wire. Now we stop that magnet, V equals 0, and the current stops. Assuming that there's some resistance in this loop of wire, the current would very quickly go to 0. Now we take that same magnet and we pull it away. We give it some velocity in this direction. And the current flows again, but it flows in the opposite direction. This has a lot to do with the magnetic flux through the loop of wire. So remember, flux, I'm going to use a B because we're talking about magnetic flux now. This is going to be equal to the integral of B dot dA over the surface. But it doesn't just depend on the flux. Let's go back and look at these again. In this case, the flux was the greatest. The magnet was the closest to the loop of wire. It had the biggest flux, the magnetic field lines coming out of that magnet. Many of them were penetrating the loop of wire because it was very close to the loop of wire. Yet we got no current flowing in our loop. Here the flux was less, but it was increasing. As the magnet moved closer and closer and closer to the loop, the flux was getting bigger and bigger and bigger. We got current flowing in one direction. And here, as the magnet moves away, the flux gets less and less and less, and we get current flowing in the opposite direction. So this doesn't just depend on the flux, it depends on how the flux is changing, the rate of change of the magnetic flux. Well, what is it that depends on the change of magnetic flux? We had a loop of wire, no batteries, no source of EMF. When we moved the magnet toward it or away from it, we would get current flowing, as if there was a battery hooked up there, as if there was an EMF induced in that loop of wire. So we say the induced EMF is equal to the rate of change of the magnetic flux with respect to time. We often have more than one loop because we're trying to magnify the effect that the changing magnetic field has on our circuit. So we would add the number of loops. Why the minus sign? Well, if you keep track of all your signs and you follow all the rules, This will tell you what direction the current flows, what direction the EMF is oriented. But I find it very difficult to keep track of all the rules for signs in Faraday's law. I find it's easier to use Lenz's law to figure out the direction. Lenz's law tells us that the direction of the EMF, or the induced current in the circuit, creates its own magnetic flux that opposes the changing magnetic flux that created it. That's a lot of words there, and it sounds a little confusing. Let's take a look at some examples. If we have a bar magnet moving down the page toward this loop of wire, the loop of wire is perpendicular to the page. I've drawn a cross section of it here, and our magnet is moving in this direction. Well, let's draw the magnetic field lines. The magnetic field lines come out like this. And as the magnet gets closer and closer and closer to the loop, the magnetic field gets stronger. More magnetic field lines are penetrating the area defined by that loop. So the magnetic flux is increasing, and it's pointing toward the bottom of the page. If we were looking down from the top, we would see the magnetic flux going away from us, and it would be increasing. So a current is going to get set up, and we have two options. That current is going to go clockwise or counterclockwise. Lenz's law tells us that the induced current is going to create its own magnetic flux through this loop, right? Because if we have a loop of wire and we run a current in this direction, that will fill the space around it with a magnetic field. What direction is the magnetic field? Anywhere inside the loop of wire? It is into the page. What direction is the magnetic field anywhere outside? It is out of the page. So when that current starts up, it adds its own magnetic flux through the loop. Lenz's law tells us that that added flux from the current that just got generated in this loop of wire has to oppose the change that created the current to begin with. So how did we get a current to flow in this loop of wire? We increase the magnetic flux down into the page through the loop of wire when we're looking down from above. So if the current goes in this direction, if I goes in this direction, it's going to add its own flux down through the center of this loop. And Lenz's law tells us that that is not what happens. It has to oppose the change. So the current has to flow in this direction. If it flows in this direction, it will create its own magnetic flux up through the middle of this loop, opposing the change that created it. Now we'll move the magnet away from the loop toward the top of the page. Again, the magnetic field lines point toward the bottom of the page. And as the magnet moves up and away from that loop, fewer and fewer magnetic field lines will penetrate the loop. So our flux is still down into the page as we're looking from above, but now it's decreasing. Decreasing magnetic flux. As the magnet moves away from the loop, the flux, the number of magnetic field lines penetrating the loop is becoming less and less and less. So a current is going to get set up to try to add more flux through the loop. It doesn't fight the flux, it fights the change. It opposes the change in flux. So the previous example, the flux was into the page and getting stronger. So the magnetic flux from the current had to try to get it back to its weaker state. It had to be up through the loop. In this case, the flux is also down, but it's getting weaker. So the current tries to get it back to where it was. It tries to get it back to a big magnetic flux down into the page. So it's going to flow clockwise in order to add its own flux to get it back to where it started, to get it back to its high flux starting point. Now we'll reverse our magnet polarity. So the north pole is up and the south pole is down. And we're going to bring it toward the loop. We're going to bring the magnet toward the bottom of the page, toward our loop. So our magnetic field lines point this way this time. If we're looking down from above, the magnetic flux, the magnetic field lines point toward us. And because the magnet is getting closer and closer to the loop, the magnetic flux through the loop is increasing. We know that in a changing magnetic flux, doesn't matter whether it's increasing or decreasing, a changing magnetic flux means we induce an EMF in this loop, and that's going to cause current to flow. The current wants to create its own magnetic flux that changes this back to its starting point. So it had very little flux coming up. As the magnet gets closer and closer and closer, we get more and more flux out of the page. So the current is going to get set up to create its own flux into the page, to try to reduce it back to where it was. We might as well finish and do the last example where the magnet is going away from the loop this time. With the south pole down, we draw our magnetic field lines. So the flux is coming up out of the page when we look down from above. But now it's getting weaker, it's decreasing. The magnetic flux is out of the page and it's decreasing. So a current is going to get set up to try to get it back to its starting point, to get it back to a lot of flux coming out of the page. It's going to go counterclockwise looking down from above so that it creates its own flux out of the page, and it adds to the flux that's there because it opposes the change. When the flux is getting weaker, it adds to it. When it's getting stronger, it subtracts from it. It opposes the change. Let's see if you've got it. Here's an example. We've got a loop of wire sliding across a table from A to B to C to D, right? Sliding across the table. And there's a region in the table where we have magnetic field going down into the table, but nowhere else. It's confined to within this region right here. The magnetic field is confined within this rectangular section, and there's no magnetic field outside of that section. So as the loop slides across the table from A to B, do we have induced current in the loop? And if so, what direction is it as we look down from above at the loop? The question is, do we have any changing magnetic flux as it moves from A to B? It has zero magnetic flux at A. It has zero magnetic flux at B. Nothing changes. So we get no induced current. As it moves from B to C, do we get induced current? we had no magnetic flux at point B. And as it starts to enter into the region of magnetic field, we start to get a small magnetic flux into the page. And as that loop moves more and more and more into the region of magnetic field, the flux is getting bigger and bigger and bigger. So we have a changing magnetic flux into the page. It's increasing into the page. So what direction does the current have to go? It has to go whatever direction makes its own magnetic field pointing out of the page. It's trying to get back to zero. At point B, it had 0, and then we push it over where it has lots of flux down through the page, and it wants to get back to its starting point. It opposes the change. So the current gets set up counterclockwise to try to create its own magnetic flux up, to fight the change, to oppose the change. Now the wire moves from C to D. We'll assume that our wire has at least a tiny bit of resistance. So if the source of EMF goes away, the current would also go away. As it moves from C to D, there is no change in the magnetic flux. It's constant the whole time. So there is no induced EMF and no current. Now it's moving from D to E. It's inside the region with magnetic field, but it's leaving. So as the tip of the wire loop starts to exit the field, the magnetic flux starts to go down. And as that wire loop moves out of the region of magnetic field, the flux continues to go down. So we have a changing magnetic flux. It was big and into the page at D. And at E, it's 0. So the current gets set up to try to get it back to where it was at D, big and into the page. So it adds its own magnetic flux into the page through the loop. All we care about is what's happening on the interior of the loop. We don't care about what's happening outside the loop. During this transition from D to E, the induced current is in the clockwise direction. Now the wire continues to move from point E to point F. At point E, there's no magnetic flux. At point F, there's no magnetic flux. At no point in between did it have magnetic flux. It was 0 the whole time. It was constant. And as long as it's constant, we have no induced EMF, no induced current.